start now. And today we start 3 lectures which will be devoted to strongly correlated systems. And today we consider 2 first examples of strong correlations, which will be Kondo effect on one hand, and there will be so-called RK. I will explain what it is. They both originate from the same Hamiltonian. But as usual, do you have any questions regarding magnetism and the topic of previous lectures? So try to systematize the knowledge of local magnetism, because we also discussed itinerant magnetism, namely para and diamagnetism, in few lectures, and I try to present it through correlation functions. Also emphasizing the importance of the fact that you spontaneously break continuous symmetry and consequence of what happens when the continuous symmetry is spontaneously broken in a system with short range interaction. Namely, we repeatedly discuss Kondo theorem and Young. So today, what we will discuss is related to behavior of the electrons in metals in the presence of magnetic impurities. It will be on the effect, and then in the second part we will discuss how conduction electrons mediate interactions between magnetic impurities and what is this interaction about. Okay, let's start the discussion, and let's assume that we have 3 electrons. So we have a metal. 3 electrons means you have a thermal surface, which for simplicity we will consider to be spherical. The shape of thermal surface is not so important, and you know that all effects where conduction electrons are involved usually involve the electrons in the vicinity of thermal surface. This is what we discussed in superconductivity. So only the fraction of electrons, say, of the order of temperature of the Fermi energy and chemical potential are involved in electron phonon interaction, temperature, or some Debye frequency if you are talking about phonons. So anyway, there are not so there are not all electrons. I mean, the electrons deep inside Fermi sphere, and this is Fermi sphere, F, are not participating in the scattering process just because it's very costly to excite electrons from very deep of the Fermi surface, since it costs few electron volts. Typical value of Fermi energy in normal metals. So suppose we have a Fermi gas as one ingredient, and we also have magnetic impurity, which means we have atom which possesses spin. As an example, one can consider iron impurities in gold or magnesium impurity or chromium, nickel impurities in noble metals. And the simplest way to describe the interaction between impurity spin, and there is a finite concentration of these impurities, of course, and conduction electron, is to write down the interaction, H interaction, in the form of scalar product of the spin density of conduction electrons. So electrons possess spin times spin of impurity sitting in the lattice position A. Since, as I said, I assume that impurity is not charged, the only way it can interact with the electron, the simplest way, is through its spin. So impurity is also assumed to be point-like, namely, it is not characterized by dipole moment or any kind of higher multipole moment. So, but as I said, there is a finite concentration of impurities. I should sum over all. So they're sitting R minus Ri. So here, sigma is 1/2 psi gamma sigma psi taken in position R. So this is electron density. Impurity. And of course I need to write down some complete constant, which I will write as J over N, which characterizes the strength of interaction between conduction electrons and impurity. So here N is N over V is a concentration of electrons. So I normalized my interaction. Okay. You see that the Hamiltonian is very simple. And what we shall do actually to try to see using perturbation theory what happens with the energy correction if we have of the Hamiltonian of that sort. This is one problem, and we shall see also using perturbation theory how two spins occupying positions at I and J interact through conduction electrons.
Excuse me. So here we have density of spin and density of impurity.
Yes, we have density of spins. One can imagine that there is modulation of spin density of conduction electrons, which, well, let me write the integral for dr, which is talking to impurity sitting in a position. So I will assume that the concentration of impurity is so small for the first part of my lecture that they don't speak, they don't talk to each other. And actually, what I will consider is effect of interaction between conduction electrons characterized by some Fermi surface with a single impurity. And in the second part of my lecture, I will assume I will allow two impurities to speak and discuss the strength of interaction between two impurity and the way that exchange integral looks like. Okay, as I see, as you will see, for the first part of the lecture, and again, I would like to advertise where we are going on. The interaction, well, the result will depend very much whether this exchange integral is positive or negative. namely if conduction electrons try to be aligned parallel to spin or try to align to be anti-parallel to the spin. Okay, so let's start with the first part, namely Kondo effect. I formulated the Hamiltonian, and this Hamiltonian, as I said, discuss the interaction of the Fermi sea of conduction electron, denoted here as psi, with a single impurity, which also has a quantum number, which is spin. What was puzzling? Why did people start to bother about this kind of Hamiltonian, and what was puzzling in experiment which attract attention to this problem? Since 40s, experimenters observed strange behavior of noble metals like gold, as I said, containing very little concentration of magnetic impurities. The strange behavior says that usually when we discuss the resistivity of the metal, its resistivity can behave in basically two ways. So this is the resistivity. And from the course of superconductivity, you know that if the metal is superconducting, then the resistivity drops at some temperature, which is the temperature of superconducting transition, and below it the resistivity remains zero. So these metals and here it's normal. These metals do not resist to the current flow, so they can conduct current without any energy losses. So this is typical behavior of resistivity in superconductors. But you know that not all metals are superconducting. For example, copper is not. The reason, if we discussed it with Professor Yevtushenko, is that in principle there are some other interactions which in the metals, like Coulomb interaction, which can prevent system to fall into superconducting state just because the repulsion between electrons becomes stronger than attraction mediated by phonons. Therefore, in metals which are not superconducting, the behavior of resistivity is just of that sort. So there is a residual resistivity which is associated with non-magnetic impurities, and then resistivity grows with the temperature, and in Fermi liquid theory it grows as T squared. And this actually tells us that if we take a metal and start to increase of its temperature, then the metal becomes more and more resisting, which is natural because friction, so to say, increases, and energy losses increases due to many reasons. For example, increasing temperature, you produce phonons in the system. The excitation is associated with a crystalline lattice, but you also produce electrons and holes in the Fermi distribution, which participate in the resistance. So this is what we expect in two types of experiment, in metals which either become superconducting at some critical temperature or remain normal till very low temperature and never become a superconductor. What was observed in noble metals, and this is a picture number 3, as I said, this is gold, for example, with iron impurities or manganese impurities or chromium impurities, cobalt, nickel, yttrium. Was quite strange. So when you come from high temperatures to low, the resistivity goes down, as it should be for normal metal when the temperature is down. However, at some temperature, resistivity has a minimum and then goes up. And non-monotonicity of this behavior actually attracts a lot of interest to physicists since, as I said, middle of 20th century, and only in 1964 Japanese physicist Kondo suggested some explanation which eventually resulted in opening so many directions in theoretical physics. So I decided to speak about this effect, which got the name of Kondo effect, and spend the lecture for. What kind of new methods and new approaches appear after Kondo? Actually, in early 80s, the problem with the Hamiltonian written here was solved exactly with a better answer. And then the huge interest to exactly solvable models arose, and one of generic models which is among this exactly solvable model is this Kondo. In early 19th, the interest to conformal field theories, so this, as I said, better than that. In 19th, the interest to conformal field theory, an application of this quantum field theory methods to condensed matter physics, also leads to many interesting results which are asymptotically exact. And again, Kondo effect falls into this category of the problems. And at the beginning of this century or at the end of 20th century, the fabrication of nano devices such as quantum dots also resulted in very big increase of interest to Kondo problem, because Kondo effect, and we discuss it a little bit later, can be responsible for controllable quantum transport through this quantum dot, namely enhancement of conductance. And in these quantum dot devices, unlike the bulk systems, unlike the system of alloys, where magnetic metal in small concentration exists in non-magnetic metal, in nano devices everything is highly controllable, and any kind of interaction, exchange integrals can be tuned by applying external parameters to the system, external fields like electric field and magnetic field. Therefore, what was given to us by nature became tunable in nano devices. Okay, so this was kind of historical remark why it is so interesting. And let's repeat Kondo arguments. And actually, work of Kondo was extremely simple. It's just second-order perturbation theory, and we will reproduce it here and see how, with a simple Hamiltonian and simple perturbation theory calculation, one can get very interesting results, and explain the puzzle which existed for several decades and has not been explained by anybody else. Okay, let's consider the scattering of electrons on the spin impurity by perturbation theory, assuming this interaction to be small. Of course, these exchange integrals are in fact small compared to Fermi energy. And to begin with perturbation theory, let's say what the small parameter of perturbation theory. So J over Fermi energy is dimensionless coupling constant, or the same as J times density of states of electrons on the Fermi energy is assumed to be much smaller than 1. Then constructing by one orders of perturbation theory, we will see what's going on at finite temperature. So you know from quantum mechanics, so if we have some interaction V and we want to proceed with the perturbation theory, then the first correction to the energy, and we start with a zero energy, which is defined without this interaction, is just matrix element of the interaction with respect to ground state, while second correction is sum over all intermediate states. Let me denote it M. Here it's E node minus M, and B node M modulus squared. Remove modulus, actually. So this is why, for example, if we are considering the correction to the ground state, which is characterized by smallest possible energy, then we know that second order perturbative correction to the ground state is always negative. Do you know that? Good. Okay, let's proceed with the same spirit, calculating correction to this interacting Hamiltonian, or corrections to the energy of ground state, which is the same. For convenience, it's more convenient to speak about interaction using this perturbation theory. So then, the first order B, it's just our interaction, which is H interaction, and the second order correction to V, let me say it this way, would be given by similar formula. I have to take summation of all intermediate state, and here it's interaction from initial to M times interaction from M to final, and here it's energy of initial state minus energy of the intermediate state. I will explain in more details what kind of intermediate states could be, but to do it, let's make the same kind of picture which we did when we consider the scattering of two electrons in the vicinity of Fermi surface. So what can happen? So let's first assume that we have electron, the particle which exists about Fermi surface, in some initial state, and after scattering process of impurity, it arrives at some final state. It can come there in two ways. First, of course, it can scatter to any state above Fermi surface and go to the final state. Let me denote this picture as picture. But there is a complementary process. Namely, it can happen, again, this is final state, this is initial state. It can happen that some electron from inner part of Fermi surface goes to the final state, and this is stage number 1, and then the electron goes and fills this empty state at the low Fermi surface. So this would be process, kind of process, which I denote as beam. And of course, I have to take a summation over all intermediate states, which symbolically are written here as M. Okay, having this picture in mind, let me write down a formula for process number A and process number B. Both are second order perturbation theory process. So here, let me denote the state, initial state of electron. So I'm interested in electron to be in initial state which scatters to electron in the final state. So I will denote initial state with the momentum P and spin sigma, characterized by projection as Z. Yes, V2 is a second order correction to the Hamiltonian H interaction, which is minus J over N. Here it's sigma times S. As I said, for simplicity, I will consider one impurity and the calculation perform a summation of all impurities.
Before we just had I mean, we didn't have initial state and final state.
So we have this Hamiltonian. I will consider it as a kind of interaction. A kind of interaction between, well, kind of potential which characterizes interaction between spin and impurity, which is minus J over N times sigma. So this is V1. But then, when electron scatters in the vicinity of Fermi surface, and I take into account this scattering, I show you that in second order, I will also have a process which is J square N and sigma S. So interaction reproduces itself times actually some function of the temperature and chemical potential. In third process of perturbation theory, again, I will have J over N cube sigma S, some function F3, and so on and so forth. So each process of scattering of the electron on spin impurity results in the same form of the Hamiltonian. So what I will need to consider effective interaction of spin and impurity is to sum all possible processes, which consist of second order perturbation, third order perturbation, and so on and so forth. But you will see that it's sufficient to look at first order perturbation theory because one can immediately say what happens with a spin if we know, say, function F2. My goal is to calculate this function, F2. So initial state is P sigma, final state is characterized by the momentum P prime sigma prime, and I will denote intermediate state by P1 and sigma 1. Namely, both the momentum and therefore energy is changed in the process of scattering, and spin projection. I mean, spin can be in state up or down and be flipped in the process of scattering. And this is what I'm going to take into account. So the first correction, 2A, can be written down as J over N square is this square of matrix element times sum over all intermediate states, which I will write as an integral over dp1, because intermediate state is p1 over 2 pi h. I have to take summation over all intermediate projections sigma 1 up and down, and then here I will have a matrix element sigma s with the projections sigma prime sigma 1, sigma s matrix element with the projection sigma 1, so prime. If you like, I can characterize not vector but projection. So I already chosen quantization exists such a way that my Pauli matrix Z is diagonal in this representation. Then I have to write a denominator, namely epsilon p minus epsilon p1, and it would be everything. Would I not forget to say that the intermediate state must be empty? So it has to be above Fermi surface, 1 minus n p1. It provides me the condition that I'm taking summation over all empty states which are above Fermi surface. This is just matrix element. This is a number which is the same as here. So probably to comfort you, I should write, let's discriminate between Pauli matrices and spin density. So now sigma denotes a Pauli matrix, not the spin density. And psi stands for conduction electron density at the origin where my impurity sits. So without losing generality, I put my impurity into the origin. So therefore, origin is a coordinate 0. So here I have the same psi sigma psi s, and all the rest is here. Psi sigma psi, psi sigma psi, where psi denotes creation operator of the electron, and psi bar or psi dagger, and psi is the annihilation operator of it. Once again, this is a picture in moment of space, which describes me initial and final state as well as intermediate state. In the coordinate state, I have impurity sitting at the point, so this is the coordinate, at the coordinate 0, and characterized by the spin S. And then spin of conduction electron scatters on this impurity, goes to the right, part of it is reflected, and what I'm going to find is correction to my effective, to my interaction of spin and impurity, and see whether it reproduces itself or not. Are you okay understanding what we are doing? Good. So this is process number 2A, and let me now write corresponding process for 2B. It's again J over L squared, sum over sigma 1, integral over dp1 to 2 pi h q. There should be factor n p1, which tells me that the state, intermediate state, is below Fermi surface. And now I will be writing all everything in numerator and denominator. First of all, as I said, the final state is E prime, so I have to write it down as EP1 minus EP prime. Then I have to take into account that permuting stage 1 and 2, so this is 1 and this is 2, and here this is 1 and this is 2, I have additional minus here. So now I collect the matrix element, which are the same sigma f, and here I have to write the matrix indexes in a proper way. So it's sigma 1 sigma, and here is sigma prime sigma 1. But you recall that collecting and calculating this matrix element, I have to take into account non-commutativity and then just take trace in the proper way. So I wrote two expressions. Now I will sum them up and calculate perturbative correction. So my 2a plus 2b is equal to, it's a j over n squared. Then, when I calculate this product, which includes summation of the matrix summational projection sigma 1, I have something which is proportional to constant plus something which is sigma s. So you see that spin algebra ensures me that the structure of the Hamiltonian reproduces itself, but in addition to this spin-dependent scattering, I have some constant. So now I start to write the functions which depend on temperature and Fermi energy, and then we make a simple calculation. So, in order to deal with the integral over pi, it's much better to come to the density of state the way I taught you, and write the density of state, replacing it at Fermi, density of state at Fermi surface. What remains here is the integral of xi, where xi is counted from the Fermi surface. Here it's psi1, since it's a p1, psi minus psi1. So this is the first integral, and it is proportional to s plus 1. This is how I take trace of spin variables. And then there is another integral. So this one, as you see, doesn't depend on anything. Temperature, whatever, it's just a number. But this one, since we have two Fermi distribution functions, is written as 2n psi minus 1 over psi minus psi 1 d psi 1. So, here, integral is taken from minus chemical potential to chemical potential, the same way here, from minus chemical potential to chemical potential. If we look at this integral, it's a principal value of logarithm, so the integral has smallness, integral is 0. In principle, it has smallness psi over Fermi energy, but since we take our initial and final states at the Fermi energy, it goes to 0. This is not the case for second integral. Let's look at second integral more carefully. And this is precisely what we need in order to look how the perturbation theory, and this is main particle perturbation theory, of course with green functions it's much easier to explain. Let's look at this integral. What it is 2n psi minus 1, where n psi is Fermi distribution function. It's 2 times e to the power psi over temperature minus plus 1 minus 1. So it's 2 minus e to the psi over temperature minus 1 divided by 1 plus e to the power psi over temperature. It's 1 minus e to the power psi over temperature. 1 plus e to the power psi over temperature. Or it is e to the power minus psi over 2 temperature minus e to the power minus psi over 2 temperature, e to the power psi over 2 temperature plus e to the power minus psi over 2 temperature. So it's a minus tangent hyperbolicus psi over 2 temperature. This is usual structure of expression which contains twice Fermi distribution function minus 1, where we take into account that we do our perturbation theory at final temperature. Therefore, if I look at this integral, I see that it is sigma dot s times integral psi 1 minus psi, and here tangent hyperbolicus psi 1 over 2 temperature d psi 1 from minus mu to mu. So as I said, we will take both initial and final state of Fermi surface. Therefore, I will take psi equal to 0, and what remains is twice integral from 0 to mu tangent hyperbolicus psi 1, let's say tangent x half over x dx, and here it's mu over temperature. If you look at this integral, what do we see? I made it dimensionless. You see that now x is dimensional variable, which is psi 1 over temperature. I divide it by temperature and multiply it by temperature. How does this integral behave? You see that in low limit there is no divergency because the tangent hyperbolicus for small x is just x. Therefore, there is no danger on low limit. However, on the upper limit, and as I said, mu is a chemical potential, which is roughly Fermi energy. Temperature is small compared to Fermi energy. Therefore, the integral on upper limit tells me that tangent hyperbolicus on it is 1. So the integral, as you see, logarithmically diverges. So I can write it as twice sigma f log mu over temperature. So this is the result. You see what happened, that although J times density of state for the Fermi energy, there is of course this factor is much smaller than 1, then the smallness of this parameter is compensated by large value of logarithm, which increases when we decrease the temperature.
Why
integral, of course, is divergent. Why? Because, well, can write integral from 0 mu over temperature tangent hyperbolic x of dx. Let's split it from integral to 1 plus integral from 1 to mu over temperature. So in the first integral, we can expand our integrand and write that this is integral from 0 to 1, and here it's x half plus divided by x dx. So this is just a number. In the second integral, I will replace tangent hyperbolicus by 1. So this is integral from 1 to mu over temperature dx over x. So it's going together. So I'm doing logarithmical theory. Of course, there might be some number like e inside of logarithm. But since I'm saying that logarithm now is temperature dependent, I don't care whether it's logarithm of mu over temperature or logarithm of twice mu over temperature or logarithm mu over 2 temperature. This additional number of that sort, of the order of 1, is not important. Why? Because I'm calculating correction. And in this correction, I take so-called leading log approximation. So what I got, the H interaction is equal to minus J over N psi gamma sigma psi S. Here it's 1 minus J over N, because I calculated second order correction. You remember it was proportional J over N squared times density of stable thermal energy. And then this number comes J over N squared density of stable thermal energy over 2. So I open bracket and write density of state of thermal energy times log mu over temperature, plus and so on and so forth. So this is what I obtained. Okay? This is in fact second order correction to the Hamiltonian, and what I'm saying is that smallness of this parameter, which assumed small from the very beginning, now starts to be compensated by a large number of logarithm, which becomes bigger and bigger when I reduce temperature. So what I have to do is to compare the zero order, well, first order and second order perturbation theory results, and when they become of the same order of magnitude, my perturbation theory breaks down. So therefore, if I write that 1 is equal to J over N times log mu over temperature, some temperature which I denote Tk, then I obtain that Tk is equal to mu e to the power minus 1 over J over N times density of state. Let's actually be more accurate. We see from this formula that the correction has a different sign depending on whether your exchange integral is negative or positive. Moreover, if J is negative, then one sees increase of conductance. So what I'm saying, if J is negative, I see that something logarithmically increases and perturbative correction logarithmically increases with the temperature. While if J is negative, it's still in perturbative limit smaller than 1, so at some temperature it will nullify the Hamiltonian, which means that if J is positive, then the scattering reduces, effective scattering, while if J is negative, then the scattering on impurity enhances. Okay, this temperature scale, which is written here, gives us the temperature where perturbation theory is not applicable anymore, because now I see that in order to calculate perturbation theory expansions, I need only this parameter to be small, but also Gn logarithm mu over temperature to be small. So this is condition of this perturbative treatment of the mode. Okay. If I write down the correction to resistivity the same way, so resistivity is a function of temperature, will be given to some constant rho naught plus term proportional to concentration of impurities logarithm mu over temperature plus in principle some constant b times Coulomb contribution, which is t to the power of 5. Of course, there are electron contributions which give you t squared, but let's say that we are at sufficiently high temperatures. So minimizing this resistivity, one can immediately find that this function is a minimum, which is coefficient between phonons and this is precisely what has been observed experimentally. So the message is that interaction of conduction electrons with magnetic impurity enhances the resistivity and results in non-monotonous behavior of the resistivity, provided that they interact antiferromagnetic, namely that the interaction is negative. What then happens? Suppose that this is a spin of impurity, and why ferromagnetic and antiferromagnetic interactions are so different. If the interaction is ferromagnetic, for example, and of course total spin is conserved, then the scattering of electron on impurity cannot result in spin flip. So both spin of electron and spin of impurity remain the same because they align parallel. However, in antiferromagnetic case, the scattering of electron on impurity can both lead to the same state or to the state where both spins of electron and impurity are flipped. Therefore, the possibility of flip of electron actually enhances the scattering process, enhances backward scattering, and therefore leads to logarithmic increase of the resistivity at low temperatures. So, summary. Nothing happened when electrons and impurity talk ferromagnetic. But very dramatic things happen if they talk antiferromagnetic. And dramatic things means that the enhancement of the interaction is temperature dependent, and if we go down for sufficiently low temperatures, the perturbation treatment becomes incorrect. And this was a reason, actually, to think about some non-perturbative treatments. One of them, as I said, Beta-Ersatz method. Another one is based on conformal invariance and conformal versus conformal field theory. And they both provide us correct result of what happens at sufficiently low temperature, which is not accessible due to this condition by perturbation theory. So what then happens at temperatures sufficiently small compared to Kondo? Our treatment, the treatment done by Kondo, is when temperature is larger than T. So what happens at small temperatures? The interesting fact is that at small temperatures, system of local moments, namely spin impurities, mimic the Fermi system. It's absolutely not trivial fact. What does it mimic fermionic system? It means that contribution to specific heat proportional to concentration of impurities is linear in temperature. The correction proportional to concentration of impurity to susceptibility is a constant, and correction to resistivity proportional to concentration of impurity is T squared. All these three facts tell you that the local system mimics the Fermi system, which is very important message because it tells us what the universality class of the law. Moreover, at sufficiently low compared to Kondo temperature, energies, the spin of impurity is completely screened by conduction energy. So this is known as Kondo cloud. So system becomes non-magnetic, although it contains some magnetic impurities. Why it is so important? Because this strongly correlated model in the limit, why it is strongly correlated? Because in the limit of low temperatures, this effective coupling constant, which we used in perturbation theory, is larger than 1. Therefore, correlations become strong and strong. So this strongly correlated system nevertheless behaves like Fermi limit. So this interesting and remarkable behavior also attracted a lot of attention in strongly correlated community because people believed that this kind of scattering becomes important